In the first blog post, we talk about the vision behind our product and the problem that we are trying to solve. Starting from the second blog post, we talk about the different features and abstractions supported by our platform. As I mentioned earlier, SelfMachines support several levels of abstraction. The first level of abstraction that we support is the layer level, and the last level of abstraction is the system level. The system level is essentially a directed acyclic graph of agents. At the layer level, we provide 50 different layer types. These layer types include the usual layer types that you encounter in deep learning frameworks, such as PyTorch and TensorFlow. In the modular extensibility blog post, we discuss about the extensibility aspect of our platform. We explain to you how you could create customized module types relying on the hierarchical graph representation provided by our platform. In the next blog post, we talk about the block level. The block level is the abstraction level after the layer level. A block construct is a structure graph of layer nodes. Putting together layer nodes as part of blocks, you could create customized data processing cascade patterns. Examples of blocks in the context of deep learning are residual blocks used in ResNets and pointwise feed-forward blocks used in transformers. Also, you could create blocks that do not rely on deep learning layers. The next abstraction level is the stage level built on top of the block level. Stage modules represent cascade data processing patterns using block modules as their building components. A typical use case of stage modules is to represent different stages of deep learning backbones. For example, ResNet backbones come with 5 different stages, and each stage of a ResNet backbone can be represented by a stage module defined at this abstraction level. So far, we have discussed about the layer level, the block level, and the stage level. The next natural step is to be able to create and define data processing directed acyclic graphs. That is actually what happens at the next level, the graph level. In the graph level, you could define any customized graph that you wish. Also, the platform comes with a number of predefined graphs, such as transformer encoders, image feature extractors, loss and eval graphs. In the next blog post, we introduce metagraph level abstraction. A metagraph is a directed acyclic graph where its nodes are the graph constructs from the previous level of abstraction. The hierarchical graph representation provided at this level of abstraction allows you to create customized graphs for your specific business needs and logics. In addition to the ability of creating your own customized metagraphs, we have developed and added a number of built-in node types with the functionalities that appear as comment patterns in different pipelines. For example, it is a common pattern to be able to bring data from different data sources into your pipelines. One of the added built-in node types is the dataset node. The dataset node allows you to bring data from different data sources into your pipelines. Another built-in metagraph is the data sync node that allows you to store the output of its attached nodes throughout the executed sessions. Another built-in node type is the chatbot node that realizes the conversational workflows. The chatbot node comes with 2 operational modes, the external API mode and the internal model mode. In the external API mode, we invoke external API calls in order to generate chatbot's answers, whereas in the internal model mode, we instantiate the LLM internally in order to generate chatbot's answers. Talking about LLMs, we have added another built-in node type called LLM. This LLM node allows you to create your own customized LLM with your own specific hyperparameters. For example, you could create a LLM with the exact number of layers that you want. Also, this node type allows you to instantiate internally publicly available LLMs such as Llama 2. Another built-in node type is the interactive input node. The interactive input node is used when you want to execute your graph in an interactive mode. Essentially, you could either execute your graph in an interactive mode or non-interactive mode. In non-interactive mode, the graph execution does not get interrupted and ends based on the defined execution sessions. In the interactive mode, however, the graph executions gets interrupted for each run, so that the users could provide the inputs corresponding to the interactive input nodes through web app. For example, connecting an interactive input node to a chatbot node, the graph execution stops, so that the users could provide the input for the interactive input node, and then the interactive input node's output will be passed to the chatbot node. Let's switch gears and talk about the training aspect of the metagraph abstraction level. In order to support the training of ML models, we have added a number of built-in node types, including loss, evaluation, and optimizer nodes. Using these nodes, you could create full functional evaluation and training pipelines. Attaching dataset nodes to ML nodes as well as loss and evaluation nodes, and attaching loss nodes to optimizer nodes, you could backpropagate gradients over the edges of your graphs while computing the evaluation metrics. The focus of our next blog post is agents. Agents are graph of metagraph constructs from the previous level of abstraction. Agents allow you to represent more complex reasoning structures. One of the main features of agents in our platform is multitasking. Multitasking is a necessary feature for agents so that they could adjust their functionalities adaptively according to environment conditions. The way that we implement multitasking for agents in our platform is by assigning a designated graph for each task. In this case, the graphs of tasks could share nodes. Sharing nodes among graphs of tasks allow them to save resources, while the ability of sharing knowledge between them. We also offer a number of built-in agents, including a train agent. The offer train agent automatically creates graphs corresponding to training, evaluation, and serving workflows for ML models, which significantly reduces their ML development cycle. In the next blog post, we discuss about the system level, which is the last level of abstraction in our platform. Systems are graphs of agents. Using system constructs in our platform, you could represent full functional AI systems. For example, a system graph could have an agent node making external API calls, while its outputs being passed to another agent node with a neural network, whose weights being updated using gradients computed by an optimizer agent, which is connected to a data source agent as the source of ground truth data. Job objects are the focus of our next blog post. We use job objects in order to execute systems defined in the last level of abstraction in our platform. We support two types of jobs, interactive jobs and non-interactive jobs. Examples of interactive jobs are chatbot workflows, whereas the example of non-interactive jobs are ML training and evaluation pipelines. Our last blog post is a tutorial demonstrating the full lifecycle use case of our platform to build an AI agent. This is an image classifier agent that relies on its internal data sources to learn image classification. This agent comes with two separate designated inference pathways for CFAR10 and CFAR100 image classification tasks. Sharing the feature extractor node among these two tasks allows the agent to perform better at these two tasks while saving resources.